We're going to welcome our next speaker, Hao Peng. He's from here at the Computer Science Department at UIUC, and he's going to tell us about open source versus proprietary LLMs. So thank you very much. Take it away.
Yeah, thanks for the intro, and thanks for the invitation. So this is how you build a large language model. Tatsu just did all the heavy lifting, sort of talking about this in his talk. Let me do the sort of a more scary portrayal of the, since it's Halloween, so why not? So it is roughly a three-stage process. The first is to pre-train the model on a vast amount of raw text data. This gives you a giant monster over there that is often called a base language model. The following fine-tuning steps aim to elicit useful capabilities out of these base models. So there are mainly two ways of doing the fine-tuning. The first is called supervised instruction fine-tuning, or SIFT. It improves the model's instruction following capabilities and also builds up its performance on the benchmark data sets. RLHF, or reinforcement learning from human feedback, is usually applied to an already instruction-tuned model and used to push it even further, primarily trying to address the safety concerns. I depict the pre-trained model with a monster, but it should not be associated with negative connotations, since it is actually a very important stage in the life cycle of a large language model. If the base model is reasonably good, it only takes a surprisingly small amount of fine-tuning to get those nice capabilities out of the models. So pre-training is unsurprisingly very expensive, and is only affordable for several big companies. Meta, along with several other institutions, had this very well-received move. They did all the heavy lifting and publicly released their pre-trained model to the community. These include models like OPT, Bloom, Falcon, and perhaps the most well-known one, Llama. So these base models provide the foundation that makes it possible for the majority of the community to actually participate in the research about large language models. It is actually now fairly affordable to build a large language model by fine-tuning. Examples of these include Vicuna, Alpaca, and many of them are actually built by universities, like Alpaca by Tatsu's group at Stanford. So new ideas have been tried out at a rapid pace. What is more impressive is that as we better understand the sort of a recipe for building large language models, the performance gets stronger, and even comparable or even outperforming proprietary models on well-established benchmarks. So people got really excited about closing the gap between the open source models and the big players. You start to see some interesting claims. Some people even gave a very sort of detailed timeline that OpenAI will lose its early starting sort of advantage and be gone in a couple of years. Of course, people will disagree, saying that we already built, 24 models that already beat GPT. So these arguments seem very bold, but if you look closely at the benchmark performance, they are actually well justified. Then I got really curious. Are we really there yet? Searching for an answer to this question actually leads to more questions than answers. And one of them is, are we evaluating the right thing? I won't be able to answer this question in this talk, but I will share some interesting findings that we had while looking for it, and hopefully they'll be fun. So before I dive in, let me do a quick poll. So show of hands, how many of you have GPT consoles like this? Really brief, one question, one answer, never going beyond one turn of interactions. Cool. And show of hands, how many of you use ChatGPT like this? A lot of revisions, clarification, and feedback to the model, and it takes many turns of interaction to actually solve the problem. Okay, if you are in this group, you are actually in great company. According to a crowdsourced data, about 73% of exchanges between user and ChatGPT have more than one turn, and involve models learning from textual feedback provided by users to solve the problems. So, however, almost all of the established benchmarks target single-turn performance with zero feedback. This is clearly a gap between evaluation in the research context and what happens in practice. So we want to address this with a new evaluation framework, and here is our wish list. Our first wish is to bridge the gap between the research evaluation and the real-world applications. How is this achieved? We want to complement conventional single-term benchmarking with models' multi-term performance, and also their performance improvements by reacting to the exchanges with the user. This is a good indicator of the model's capabilities of faithfully following instructions and learning from the user's feedback. So to put this into more details, I have a running example on how this is reflected in the design choices of our evaluation framework. The user opens with a prompt. The model is then supposed to generate a thought process of how to approach this problem. Some people call this chain of thought. I usually see this as a justification of the model's outputs. It helps interpret the outputs and can also improve the model's performance. The user then stares at this intermediate thought process and gives feedback to the model, including both a binary label, whether this is correct, and the natural language feedback. In this case, the model did something wrong. And then the model gives another try. In the next turn, this process is repeated until the model finds a solution, correct or not, or it reaches the limit on the number of turns. So this is our natural language interactions. This process can be optionally augmented with Python code generation, which allows the model to use external tools. Tools help them to sort of improve the performance and also make it possible for them to interact with a calculator, or a website, or even the physical world. So our second wish is to have a comprehensive evaluation. This is more straightforward. We include a diverse set of tasks. 8 data sets spanning 4 different tasks, including mathematical reasoning, question answering, code generation, and decision making. So I won't be able to go into the details here. These are all well-established benchmarks that the community have been pushing for. We only include the more challenging sort of instances that the model are less likely to be able to solve without any feedback. So when we look at these results, numbers will be sort of much lower than what you are super familiar with. Collecting feedback, user feedback, is actually very expensive. Our third wish is to do this without breaking the bank. To achieve this, we never annotate any new data points, but a response just repurpose sort of high-quality established benchmark data sets. And besides, we use GPT-4 to simulate human natural language feedback instead of actually sort of hiring the annotators to do this. This practice has become more and more well-received, and there is actually an increasing amount of evidence that GPT-4 does better at this than average humans do. So, for example, we did this human eval, basically trying to compare the helpfulness and the human-likeness of sort of GPT-4 generated and the human-generated feedback. It turns out GPT-4's feedback is much more helpful than human-produced ones, which is not surprising. And it is kind of interesting to see that GPT-4 generated texts are considered more human-like than human-produced ones. This is the basic design of the evaluation framework. It looks pretty intuitive, but it actually involves tons of engineering efforts, which I have to cut to not bore you to tears. We compared a lot of models. I have 20 of them on this slide, but I'm pretty sure we did more than that. My collaborators are so hardworking that I keep adding to this list, and I lost count in the end. So the selection of these models is actually carefully thought through. We want to answer questions like what kind of role model sizes play in this, and does sort of do different training techniques make a difference, including SIFT or RLHF, and is there any performance gap between proprietary models and the open source ones? So before I dive into the results, let me brag about this website that my collaborators built. It's awesome. If you have your laptop or your cell phone at hand, please take them out and check this out. It's far more interesting to sort of interact with this website than sort of hearing me walking you through this. I will pause for 10 seconds here. Okay, so yeah, this is the results. The performance is micro average across the 8 data sets we just talked about. The red bars are the performance with up to 5 turns of interactions, and the blue bars is the improvements by including GPT-4's natural language feedback on top of that. The proprietary models are on the left-hand side, and the open source models are on the right. So all open source models here are fine-tuned from Llama 2 with various sizes. The table at the bottom sort of tells us sort of whether these models are fine-tuned with SIFT or ROHF. The first trend we can see is that even the best sort of performing open source model underperforms all of the proprietary models, except POP2 by Google, and which actually underperforms half of the open source models on this figure. So when we break down the performance by the number of turns of interaction, things become slightly more interesting. So the way to read this figure is that each point is the micro average performance under the budget on the number of turns. So it's basically, and the number of turns is depicted on the x-axis. Basically, if I give you 3 turns, for example, what's the best you can do? Llama 2 and its fine-tuned version, Llama 2 Chat, both outperform GPT 3.5 if you only consider fewer than sort of one turn of interactions. And Llama 2 even beat GPT 3.5 for up to 3 turns. But this trend is actually reversed when we allow more interactions, and the GPT 3.5 does a better job in terms of learning from the textual feedback through the interaction with a user. And even more intriguingly, so although Llama 2 Chat achieves the best performance with fewer turns, it actually performs the worst if you allow sort of 5 turns of interactions. Recall that Llama 2 is actually the base model. Llama 2 is the base model of Llama 2 Chat. The chat version has undergone sort of instruction fine-tuning in the ROHF, which are designed to boost its performance on benchmarks. But it actually hurts the performance here. Something must be wrong, so we decided to take a closer look. This trend is actually very, very consistent. If you compare all the Llama variants here, SIFT and the ROHF actually hurt the model's multi-turn performance. And this happens in terms of both their absolute performance in the red bars and the capabilities of learning from natural language feedback in the blue bars. This applies to both Code Llama and Llama and Vicuna across all sizes, and these variants are actually fine-tuned by different research groups. But Lemur is shows the opposite trend. Lemur is another model fine-tuned from Llama to 70 billion on code data and provides an instruction fine-tuned variant. So contrary to the previous slide we just saw, the SIFT version of Lemur actually does outperform its base version. So our first hypothesis is that there could be something wrong with fine-tuning data used by this model. So we took a closer look. We find an interesting and strong correlation between training on a data set called shared GPT and producing a specific type of errors in the model's outputs. So shared GPT is an open source data that collects volunteers' chat history with ChatGPT, and it is used by almost all open source models in fine-tuning. Vicuna is primarily fine-tuned on shared GPT, and they are more sort of likely to confuse underscore with escape underscore while generating Python code. And this causes a lot of syntactic errors since escape underscore cannot be parsed by Python interpreters. And Lemur also trains on shared GPT and also commits the same type of errors, but far less sort of frequently, for about 2.2% of the outputs. Models trained without shared GPT never commit this kind of errors. So it turns out that 15% of the instances from shared GPT include escape underscores. We conjecture that this issue is an undesired artifact caused by their sort of data pre-processing and have been sort of negatively impacting the open source models especially on the code generation performance. So Vicuna bears a larger impact since it fine-tunes only on shared GPT, and its larger version is worse than on this since it overfits to this artifact. And the lemur is less affected since shared GPT only accounts for a tiny portion of its fine-tuning data. And now for the llama models, they train on in-house data collected by Meta. We conjecture that this data is suboptimal for the multi-turn performance. We don't have concrete evidence for this since we don't have access to their data. Their technical report says that their RLHF is used to train Llama 2 chat and both Llama 2 chat and Code Llama is multi-turn dialogue. And we think that they did not consider models multi-turn performance while during the quality control phase while collecting these data. Another interesting finding is about the 2 generations of the cloud models. So in case you haven't heard about cloud, it is a model built by a company called Anthropic. They are founded by former OpenAI members. It is the only serious competitor to GPT today and actually does better in many applications. Surprisingly, the more recent cloud version 2 actually underperforms its predecessor. So breaking down this performance across multiple turns, Cloud 2 outperforms its previous generation counterpart with fewer than 2 turns, but the trend got reversed with more than 3. This suggests that there might be some sort of oversight of the model's multi-turn performance, even for some of the leading players in this field. And finally, perhaps unsurprisingly, using GPT-4 to provide feedback for yourself does not help. You cannot see this from this figure, but the blue delta here is actually negative. The trend is actually very consistent. We found that all models barely benefit from their own feedback. Although models do not learn from their own feedback, they can still benefit from weaker models' feedback. In this figure, we use different models to provide feedback to GPT 3.5. We can see that the 2 Code Llama variants can give useful feedback even when they are substantially underperforming GPT 3.5. So there's still a huge gap to the feedback provided by GPT-4. So a recap, multi-turn performance complements conventional single-turn benchmarking and better reflects real-world applications. SIFT and the RLHF, if executed improperly, can actually hurt the model's multi-turn performance. We have evidence suggesting that open source fine-tuning data does better than Llama 2's in-house data in terms of improving models in multi-turn performance. But we found that something weird about shared GPT's data collection procedure, which might be hurting the model's training on it. And multi-turn performance is often overlooked, possibly by even the leading players in this field too, and it deserves more attention. Do we have questions before we shift gears? Okay, so in the first part, we had this interesting finding that language models can often improve themselves upon receiving feedback from an AI agent without human involved. What does this remind us of? I've put a pretty subtle hint over there on the slide to help you make the guess. So in many ways, this capability reminds us of a textual counterpart of AlphaGo. So in the second part, I'd like to discuss some of our exploration of language models' potential to continuously improve themselves through self-play without direct human intervention, or the lack of it. So why do we care about this? First of all, it is fun. It happens to have some practical benefits too. As these models get better, it will be increasingly hard to improve them with the human-produced data. This is reflected in both the pre-training and fine-tuning stages. I've heard rumors that GPT-4 has already exhausted all the internet textual data, and they have to resort to image and videos to properly pre-train the model. And that's the model outperform average human on many tasks. It's getting more and more expensive to collect high-quality human instruction and preference data to keep improving them. Using models to improve themselves can be a neat solution to all of these issues. So let's specify some connections between AlphaGo and today's large language models. AlphaGo is optimized for a very clearly defined goal, and it trains on the data generated from self-play with the reinforcement learning. The goals that language models are trained to achieve are less well-defined. They can learn from AI feedback through in-context learning. To emulate a self-improving agent, we need to find a setting where language models can borrow something from the AlphaGo's success recipe. Our choice is the text-based games. They come with clearly defined rules and goals, and the language models can compete with themselves and improve by in-context learning from feedback generated by AI agents. We spent a lot of time on this, exploring different options, and we found that most text-based games turned out to be too challenging for today's large language models. So for many of them, we couldn't even get the models to understand the rules of the game and get it started. So we also tried established cases from game theory and debate. For these cases, the models do better, but we couldn't find a way to properly evaluate their progress. So we then asked ourselves, okay, what's the easiest thing we can come up with? And that leads to a minimal bargaining game. It is extremely easy by design, and I challenge you to find an easier game, and I will bet you a balloon for that. So this game has 3 roles: a buyer, a seller, and a critic. The rules are really, really simple. The buyer wants to buy a balloon from the seller. They play against each other through a negotiation game. They basically negotiate with each other, trying to get a more favorable price for this purchase. For the buyer, the lower the price, the better, and for the seller, the higher the better. So the buyer and seller's performance is evaluated using the deal price they finally achieve. The critic acts as a coach and gives feedback to the 2 players to help them improve their negotiation strategies. And each of these 3 roles is played by a different language model. So let me strengthen the motivations of this bargaining game. It is easy enough for the models to actually understand rules and to start playing. It's a competition between these 2 models and have a clear goal and rules and a way to evaluate their performance. And it also makes it easy to track the model's improvements through learning across multiple rounds of games. Here's an example. In the first round, the buyer and seller start off with some basic conversations about the purchase. The starting price is forced to be $20 through prompting. And also, I'm only showing 2 pieces of text, but it actually continues until this model reach or break a deal. And for each round, after each round, the entire chat history is fed to the critic model, which provides natural language feedback to only one of these 2 players. The other one never received any feedback. Presumably, we're trying to quantify how this can help the one who received feedback to improve its negotiation strategy. And we repeat this process until the limit on the number of rounds of the games is reached. We tested all of the state-of-the-art models that we had access to during the time of this project. We already talked about the GPT in the cloud. Jurassic was built by a startup called AI21. It can play the game, but only for 1 turn. The Cohere one was extremely strong on the benchmarks, but we couldn't find a prompt to make it understand the rules of the game and start playing. But it made a lot of hilarious mistakes in our experiments. And one of them was that when Cohere plays a buyer, the balloon starts with $20. Cohere buyer, the very first output is that I'd like to buy this balloon for $25. It didn't work, but we had a lot of fun playing with Cohere. These 2 models are dropped in our experiments for these reasons. We also tried open source models. Same issue as the Cohere model. None of them worked. So let's look at some results. The x-axis here is the range of the final deal price. And the y is the frequency of that being happening. So for each setting, we run 500 sort of simulations and plot the distribution of the final deal price. The blue bars are the distributions before receiving any feedback, and the orange ones are after the sort of feedback from the critic. The way to read this figure is that going from blue to orange, if the distribution shifts to the right-hand side, it means that the deal price increases overall. And that indicates the seller is improving its performance by learning from the critic's feedback. We can see from these two figures that both Cloud Instant version 1.0 and GPT 3.5 can indeed improve as a seller receiving sort of critic's feedback. Buyers, sort of playing the buyers is actually harder. We see these four figures are similar, only that the models here are all playing the buyers. So going from blue to orange, we are expecting the model to shift the distribution to the left. If that's not happening, it means that the model playing the buyer is not improving. And that is indeed the case for Cloud 1.0. And sort of the three sort of other models actually sort of do better on this, and the GP4 is the best one on this. So this is sort of breaking down the performance changes over multiple rounds of game. Cloud 1 only improves for one round, and all other models improve for multiple rounds. And GP4 achieves the best sort of performance overall. There are many other interesting findings in the paper which I don't have the time to sort of go through here. This bargaining game turns out to be an interesting way to qualitatively compare the capabilities of these models. Everyone can chit-chat. Being able to understand the rules and start the game already rules out all of the open source models and some proprietary ones. When we make this more challenging and expect the model to be able to learn from AI feedback for multiple turns, we see there are three clear leaders from this plot. So the takeaways. OpenAI and Anthropic are the sort of clear leaders, leading players in this field. Their models are probably several generations ahead of everything else. For other players, especially the open source models, strong benchmarking performance often fails to sort of translate to scenarios that these benchmarks do not cover. And it is perhaps a good time to rethink what we are optimizing for and evolve our evaluation protocols alongside our models. So evaluation is so hard. I'd like to close with an ongoing effort with a sort of very misleading name, COT Hub. So it stands for Chain of Thought Hub, but Chain of Thought is actually only a small portion of this. COT Hub aims to build a crowdsourced evaluation platform for large language models. We know that evaluation for large language models are super challenging and ever evolving, and it takes dedicated and a long-term effort to sort of to maintain this, but it usually receives less appreciation than what it deserves. COT Hub wants to defer this maintenance effort to the evaluation platform to the crowd, asking the practitioners to contribute to this effort. To make this happen, we made it extremely easy to add new models and the tags by design. We have also made efforts on the quality control, such as sort of standardizing the prompts we provide and requiring the code submission for reproducibility. We have already received sort of many contributions from practitioners around the world, and please consider sort of helping us keep this going. Many of our decisions are suboptimal, but we are very open to any suggestions, especially on finding a better name for this. Okay, cool. This is all I have. I'm the guy that talks a lot, and this is my awesome collaborators that did all these sort of awesome works. Thanks for your time, and happy to take questions.
Hi, great talk. I was wondering, in terms of the games that you thought of, did you consider like actual text games like crosswords or like anagrams and these sorts of things, because they seem to combine like reasoning as well as language skills, and and if you could get the models to play those or how they failed.
Right, we did consider that. We tried several things, several games that the authors know how to play. We couldn't make it work. There was, I think, the follow-up work by, I don't know, Hao Peng, that makes a sort of a GPT-4 to be able to play with Dungeons & Dragons. They did tons of engineering to make that happen, which we were not able to achieve during the time. But I think there has been another follow-up by, I think, colleagues at AI2. They were able to make these models to play some auction games, which is also pretty elementary, but it's probably more interesting, more real world than this sort of bargaining game. So to answer your question, I think this is indeed possible. We considered that, but we couldn't make it work at the time. But I think there are chances that with more engineering effort, this can happen.
Cool. So I saw in the first part of your talk that the base models for Llama were doing quite well, which is somewhat surprising because getting base models to do anything is a bit of a challenge. Like, is this base model with like really specialized prompts and like other tricks to get it to do anything for this task?
Okay, so I think what I know is that all the models use the same prompt. Whether or not that is heavily engineered to make Llama 2 work, I don't think so, but I need to check with my collaborators. So these are, as I recall, these are pretty standard way of prompting on these tasks.
Okay, cool, thanks.
Maybe I just missed this part, but when you were testing this bargaining game, was there like multiple rounds of bargaining? Like, say you focus only on giving feedback to the seller. So once you put a price, does it give the chance to the buyer to reject or accept that before the feedback comes, or is the feedback?
Yes.
Yes.
We do consider for multiple rounds in sort of a bargaining negotiation. I only these two pieces of text will just continue until say, hey, we should settle for this price, or no, I will walk away. I don't want to do this. So I only showed two pieces of text, but it's actually it's much longer.
And so I guess a follow-up question that I have, was there like, so you focus on giving feedback just to each one separately, right? Or do you also focus on giving like feedback to both of them in your own private channel? Because the reason I'm asking is because since you have like inspiration by self-play, when you're in a game, you get immediate feedback, and that's that interaction among your own is that gets to the equilibrium, right? So here, I wonder if you also try giving feedback to both separately. Both the buyer and the seller. Yeah,
that's a great suggestion. So we did this. So we fixed the other player primarily to do some control experiment to see, the one that actually received the feedback, are they able to improve by conditioning on the feedback? I think the suggestion is great. We didn't try anything like that. I think it'll be interesting.
Yeah, because I was just wondering if maybe they never come to a settle, right? Because
it could be. It could be. It actually happened. So we set a sort of the cap on the maximum sort of rounds they can go.
Thanks.
And do you think various self-bargaining, self-improve bargaining can demonstrate that language models can self-improve their capabilities?
Sorry, so could you repeat that?
And do you think, based on the result of self-play on bargaining, do you think whether language models can self-improve themselves?
Yeah, I think I think I'd like to answer that in the positive. I can expect some challenging to this argument, especially I've seen something like this is pretty toyish, and does this actually translate to anything useful in practice? In this work we don't have any evidence for that, but I think that could happen in practice. But I also think there's like the cap on the best you can do by keep doing this, which will be reached with a sort of maybe not surprising high number of turns.
Mm-hmm. Okay, thank you.